What's going on, guys? My name is Amos and I'm back again with another video. So in this video, we're going to be talking about sequences of real numbers. Now, before we even start talking about sequences of real numbers, let's first of all define what a numerical sequence is. So a numerical sequence is going to be a mapping from some subset. So let's say we have some mapping. Now, let's say we're going to call it F, for example. So a numerical sequence is going to be a mapping from some set from some subset of the set of natural numbers, into some field f that we are calling f, right? And then what this is going to do is that it is going to associate to every natural number n some real number, some number a sub n, like so. So this is what the definition is saying. So this is what a numerical sequence is. Now here we're talking about real valued sequence. Now what this f represents here is this f can either be the complex numbers or the real numbers. Now since we're talking about sequences of real numbers, this f here is going to be equal to the set of real numbers. So this is just a real number here, and then this is just some natural number in the set n1, which is going to be a subset of the set of natural numbers. Now in terms of notation here, a sub n here is just any real number. But then if we add the curly braces here, then this is going to become a sequence. So this is what the definition here is saying. Now let's first of all talk about stationary sequences before we go any further. Right, stationary sequences are going to be sequences that are going to be constant, or that are going to have the same term, that are going to have the same real number. Let's say a sub k, starting from a certain range. So let's say we have examples of stationary sequences. So here, let's say stationary sequences, and then we can talk about, we can write a few examples of stationary sequences. Now the sequence, for example, 1, 1, 1, 1, 1, 1, and then we have the ones continue. So this is a stationary sequence because we can see that all the terms, all the numbers are the same here. So we basically have a 1. Now this is a stationary sequence starting from the very first term. Now this is going to be a0, and then this is going to be a1. Now this is going to be a2, and then this is going to be a3, and then we have the other terms there. Now we can also have a sequence like this one, for example. Let's say we have 2, 3, 4, maybe 5, and then we have 1, 1, 1, 1. Now this is also a constant sequence, but then starting from this term here, So if this is your a0, and then this is your a1, and then this is going to be your a2, and then this is going to be your a3. Then starting from a4, we can see that all the numbers are the same. So this is basically going to be another constant sequence. So the sequence doesn't have to be constant starting from the very first term. It has to be constant starting from some term. If we have the same number starting from some term, which is not necessarily the first term, then the sequence is going to be a constant sequence. We also have sequences that are going to be sequences of positive numbers, sequences of real numbers that have positive numbers. So we're going to say that we're going to have a sequence of positive numbers. So let's define a sequence of positive numbers. So we're going to have a sequence of positive numbers if for all values of n in the set n1, which is going to be a subset of the set of natural numbers, if for all values n in the set n1, which is a subset of the set of natural numbers, if we have that, every real number s sub n that is going to be mapped to this n that we have here, if every such real number is going to be greater than or equal to 0, then this is going to be a sequence of positive numbers. So this is going to be a sequence of positive numbers. Now, similarly, we can now define a sequence of negative numbers. So we can have what is known as a sequence of negative numbers. So we can also have what is known as a sequence of negative numbers. So negative numbers, like so. Now this is basically the other way around. So if for all values n in n1, which is going to be a subset of the set of natural numbers, if we have that every real number that is going to be mapped to every n here, if every real number is less than or equal to 0, then this is going to be a sequence of negative numbers. Now let's talk about the equality of two sequences. So when are two sequences equal? When can we say that two sequences, s sub n and b sub n are going to be equal? So here is the definition. So let's say equal sequences sequences, and then for reference, then maybe we can, do something like this. So equal sequences. So we say that the two sequences A sub n and B sub n are equal. So if are going to be equal if for all values n in the set n1, which is going to be a subset of the set of natural numbers, if for every n we have that, A sub n is equal to B sub n. If this is going to be true for all values of n in this set n1, which is going to be an infinite subset of the set of natural numbers, then the two sequences are going to be equal, right? Now let's talk about different ways of representing sequences. Now there are many ways of representing sequences. So here let's talk about representation. So how do we represent sequences? Now the first approach is going to be, you'll be given a general term for some sequence. Now they'll say, maybe let's say maybe A sub n is going to be equal to 1 divided by n. Now this is going to be for some n in the set, so n star. We basically have to exclude 0 because we are basically performing some division here, and we know that division by 0 is going to be criminal. So every term of our sequence is going to be given by the general term 1 divided by n. Now this is one way of defining a sequence. Now this is what is known as the explicit definition of a sequence, where you're given the general term. Now another representation is you'll be given, maybe let's say some u0 is equal to some starting number. Maybe let's just say 2 as an example. And then what will follow is going to be some recurrence relation that is going to help you find, subsequent terms of the sequence. So for example, then they'll give you this recurrence relation, un plus 1 is equal to, maybe let's say 1 divided by 2 plus maybe 3 un. They'll give you some recurrence relation. And then since you have this and you have this recurrent relation, then you can find the subsequent terms of the sequence. Now this is known as a recurrence relation. And then this is going to be the starting term, right? So this is going to be the starting term. Now of course there are many things that we cannot talk about, but for the purpose of this video, these few details or these few pieces of information are going to basically do justice to they're basically going to do justice. Now let's look at the graphical representation of let's first of all maybe define the limit of a sequence. What is a limit to some sequence? What is the limit of a sequence? So we have this very long definition. Now I'm going to make sure that I sort of like explain this very long and scary definition to you in a very simple manner, right? Now the first part here is saying, so we call x the limit of the sequence x sub n. Now remember that the notation we've adopted here is we want to use the curly braces here, but this is basically the same thing, right? So we call x the limit of the sequence x sub n, which is written, x, the sequence xn is going to go to some number x as n goes to infinity, or the limit as n goes to infinity of the sequence x sub n is going to be equal to x. Then this is the formal definition, right? So this is going to be the case if for each real number epsilon, so for some positive real number epsilon, which is usually taken as a very small number, right? Which is a very small number. Now there exists a natural number n, and if we attempt to go beyond this n, then all the terms of my sequence are going to be in the region as we are going to see, x plus epsilon, x minus epsilon. So basically here, what we have here is that the sequence is basically going to approximate the real number x to within epsilon. So this is what we have here. And then this is the mathematical statement here. Now this is just me using the English language, but then this is the mathematical definition that is very concise, and it basically means whatever is written here on top here. So for some positive number epsilon, we can find some natural number in the set. We can find some natural number, and then if we go beyond this natural number n, then the sequence x sub n is basically going to approximate this real number x. Okay, now this real number is the limit of the sequence to within epsilon. And then if such a number exists, then we're going to say that the sequence is going to be convergent. Otherwise, the sequence is going to be divergent, right? And then let's look at the diagram here and basically see what is happening here. So look, all the dots that we have here, let's first of all talk about, let's first of all look at this diagram, and then we can now move to the first one. Now, if you look at the first diagram here, let's examine what we have here. Now, all the dots here represent the terms of my sequence. All the dots here represent the terms of my sequence. Now, we can see here that starting from this point here, what we can do is this, starting from, now that's not very precise. Now, starting from this point here, now we can see that all the terms of my sequence are in the region a plus epsilon, a minus epsilon. Now remember here, in the definition we have x sub n, but then what we can do is that we can give ourselves some a sub n and then minus a. Then it's basically going to be the same thing. Now, if you look at this expression here, now let's first of all try to develop this particular expression. So what if you get rid of the absolute values, then you have minus epsilon and then less than a sub n minus a and then less than epsilon. Now what we're going to do is that we're going to add a throughout, and then we're going to have a minus epsilon less than a sub n, and then we're going to have a plus epsilon. So we can see that all the terms of my sequence are going to be in the region, like all the dots are going to be in the region a plus epsilon, a minus epsilon. So if we go beyond this n, so for some n taken for some n that is large enough, we see that all the terms of the sequence are in the region a plus epsilon, a minus epsilon. Now, in general, if you choose a smaller value for epsilon, if we choose a small value for epsilon, then this n is going to get bigger. So as we can see here, we see that here we have some n0. Beyond this n0, we see that all the terms of the sequence are in the region. If we go beyond this n0 here, what we notice is that all the terms are going to be in the region. Maybe let's say this is going to be in the region a plus epsilon, a minus epsilon. So this is going to be a plus epsilon, and then this is going to be a minus epsilon. But then if we choose a smaller value for epsilon, which is epsilon 1 here, now we see that now our n, we need to choose a larger value for n. Now in this case we have some n1. Now if we go beyond this n1, we observe that all the terms of my sequence are in the region a plus epsilon 1, a minus epsilon 1. So that's all there is here. So to summarize, what we're saying here is the sequence here, if we, for some n large enough, so as n goes to infinity, what we observe here is that the sequence a sub n is going to approximate its limit, which is a, to within epsilon. So to within epsilon. Now this approximation can be made as accurate as we want, or as accurate as possible, by taking a very big value for n, which is going to imply that we need to choose a smaller value for epsilon, and then the approximation can be refined in that particular way. Now, thank you guys for watching, and I'll see you in the next video where we'll be talking about other things about sequences. Thank you guys.